For this video, we're going to start back at the beginning again with just an op amp by itself, and we're going to work all the way to an example of a feedback oscillator. So if you remember, the op amp by itself is a very high gain differential amplifier. It'll amplify even the slightest difference between these two inputs, and the gain can be like 100,000 or something like that. If you're using it in this formation where you have no feedback to control the gain, you would be using it as a comparator in this case. So this example we have just sitting there, an op amp by itself, if you were going to try to use the inputs, it would do a good job of comparing which input is greater, because it'll take even the smallest difference, amplify it by 100,000, send you right to the rail. Remember, if the positive or the non-inverting input, the plus sign here, if that one's greater, you'll head to towards the positive rail. Not quite get there, but you'll be right up against the positive rail. And if the inverting input, if the input to that is greater than the non-inverting input, if this one's winning, even by a millivolt, you'll be pegged against the negative rail. So the output goes high or low and tells you which input is greater. So, I mean, that function is a comparator and very useful, but that's with what we would call open loop gain. You're using it as with an open loop, no feedback loop is there. And then, if you remember, we wanted to create an amplifier, so we had three different formations that we used to create a negative feedback amplifier. You have to use negative feedback if you want to reduce the gain. Positive feedback will do something else, and in fact, it's going to do what we needed to do for this video, to create a feedback oscillator. But step one is to control the gain, to reduce the gain. Remember, we take RF and RI, and we're going to crush the gain down. So by whatever amount of feedback we choose. And now, this is our RF, RI. And let's just take that to circuit common. Okay. Now it's no longer a comparator. I mean, now it is an amplifier, right? So we have an amplifier. As soon as we reduce that crazy amount of gain to something usable by using negative feedback, we've turned the op amp into what we would call an amplifier, a negative feedback amplifier. And now we'll show you what happens if we add positive feedback to an amplifier. And I think we mentioned it when we did the different negative feedback amplifier types. But it's going to be a path that we create that brings us from the output back to the non-inverting input. And we'll talk about this path. It's very much like if you took a microphone, which was the input to an amplifier, and you brought it around in front of the speaker, which is the output. So the output of the amp is coming into the microphone and being fed back to the input, and you'll get a sustained oscillation, the squealing or whatever is coming from the system. So, but it's a sustained oscillation. So it's very much the same thing. Any type of positive feedback, and by positive feedback we mean that it's in phase, it's reinforcing, it's not going to cancel, it's going to reinforce and be a positive addition. So that's what causes the oscillation. So what the answer is, we use negative feedback to get an amplifier, and what happens if you add positive feedback to an amplifier? You get feedback, which creates a sustained oscillation, and that for us is going to be a feedback oscillator. Now we want more control over this feedback. We don't want to just let random uh, frequencies occur like you would have with the screeching and howling of a microphone in front of a speaker. That's not a tuned feedback system. That's just whatever's feeding back, whatever can, and so you get all different frequencies. Um, or sometimes you can get just a single frequency depending, how you're holding the mic and so on. But we want to have control over that, so we're going to put a specific feedback path here to get a specific oscillation that we want. Of course, there are lots of ways to create a feedback oscillator. For this example, we are going to use our bandpass network from a previous exercise. Um, this is that low pass, high pass Wien network that we developed, where we kind of cascaded a low pass and a high pass, and then we found it interesting, at least I do, that you can rearrange that and sort of have a circuit that looks like you laid them on top of each other, and it works the same, and that's the Wien network. Anyway, it's a bandpass network. So what we're doing here is we're providing a positive feedback path that is best for one frequency and only one frequency. So there is the center frequency of this bandpass network is going to get the easiest time of getting back around. So it will have the highest level. It will also be the one frequency that is in phase, so it has 0 degrees of phase shift, which is also important. So it'll be the highest amplitude and also in phase completely. And for that reason, the center frequency of this bandpass network is the frequency that this feedback oscillator will oscillate at. So we've done the job of a frequency selective positive feedback path, which selects one frequency over all others. That is the frequency of oscillation for the oscillator then. If we keep our same values for our resistors and caps, we'll have a center frequency of 1.59 kilohertz. That is the frequency of oscillation that will show up at the output. And right here, I think it's important to emphasize, this is the whole thing. This is the whole thing of the circuit, because a lot of times I get asked by students, well, wait, where do I hook the signal generator? So that's very different. There is no signal generator to be connected here. This is the signal generator. It's an oscillator. It produces a sine wave, so you will not be using a signal generator to inject a waveform like a sine wave into the circuit. There is no input for this circuit. This circuit generates. It is a signal generator by itself. It will generate a sine wave right here for you. And the sine wave will be 1.59 kilohertz generated by the circuit. So very different. Turn your wave generator off for this exercise. You will be building a wave generator. This is known as a Wien bridge oscillator, and it's a classic circuit. And I think we mentioned Hewlett-Packard, the company, got its start by putting together a low distortion sine wave oscillator that was a Wien bridge oscillator, and that was their first piece of test equipment on the market, cornered the market for its low distortion, and put Hewlett-Packard on the map. There are a couple more details, though, before we can get this thing to actually work. Yes, that's our goal, a sine wave at 1.59 kilohertz. We've done the frequency selective part, but now you have to remember one thing about, for this example, one specific thing is with the Wien network, you have an attenuation here of 1/3. So let's look at what we have to do to address that. The bandpass quality of the network does its job by being frequency selective. So we will have this part accomplished. We'll have a specific frequency selected for the oscillator to oscillate at. However, the attenuation of the network being 1/3 is not going to sustain oscillation. In fact, what would happen if we didn't do anything about it is you would have, if you could get it started, and that's a question, but it would die out, and just go to a straight line. It's not going to be able to sustain oscillation because of the attenuation. The feedback loop needs to be something that's strong enough to keep it going. A fancy name for the issue that we're going to solve is the Barkhausen criteria. And it simply states that whatever the attenuation is of your feedback path, you have to match that with an appropriate amount of gain so that the net result is you can keep the oscillation going. So you have to make up for the attenuation with the appropriate amount of gain for your amplifier. That's what will sustain an oscillation. It's what will keep it going because there will be losses in the feedback path, the positive feedback, and you make up for those by adding gain to the amplifier, and now it'll be self-sustaining. If you look at our gain then, here's a time you don't want to forget about this, although I often do. If you think about it, our feedback is coming in to the non-inverting input. So don't forget that +1. So when you're picking resistors to set up a gain, it's true we need a gain of 3 because we've got, what do we have, 1/3, and we've got 3, and that's going to equal 1. So we do need a gain of 3, but don't forget, since we're coming in on the non-inverting input, we already have +1 in place. So any ratio of 2 to 1 will get us, 2 plus 1 is 3. So we can put something here. I mean, just for an example, 20K and 10K. And I always have to, I catch myself sometimes, putting 30K and 10K, and that would give me a gain of 4. And I'll show you what happens if you have too much gain. Also, the Barkhausen criteria explains this. I mean, it's a simple concept, but got his name attached, probably early experimenter in feedback oscillators. So let's show you what happens if it is too much gain. So too much gain, you'll definitely get the oscillation going, and in fact, it's going to keep growing until you're going to hit clipping. Actually, you'll hit the limits of the rail voltages, and you'll start getting distortion, and it won't be like a sine wave. It'll start getting flat spots, turn into a square wave. So that's what can happen if your gain is too high. In other words, for the Barkhausen criteria, if you're greater than 1, the output is going to grow to clipping, And we said before, if you're less than 1, you're not making up for the attenuation sufficiently of your feedback network. Might not start to oscillate at all, but even if it would quickly die out into nothing. So it's a little bit of a tricky business. With this particular example of a feedback oscillator, you do have a pretty easy time creating the bandpass network, I think. But then this Barkhausen criteria is no joke. It's not that easy to hit it right on 1, and you'll find that experimentally that even though it's a simple concept, it's one of the challenges of a feedback oscillator because, like we say, there's no margin for error. It has to be exactly 1 so that it'll stay at a nice sine wave shape. And if it's a little over altogether, then there you go. You'll eventually get some distortion. And if you're a little bit under, well, it won't start or it'll die out. So this is a simple concept, but it is a challenge to solve the problem of maintaining the perfect amount of gain that matches the attenuation of your positive feedback network. For our initial experiments in the lab, uh, if you have a variable resistor that you can use, I know we're at home right now, so but that would be one way you could play with this oscillator and probably get it going if you can finesse the 20K resistance a little bit and hit that sweet spot where you have this equal to 1. Uh, I actually got lucky probably, but I tried just um, uh, two 10Ks and one 10K. I tried 20K and 10K fixed resistors, and it did oscillate. It grew to a little bit of a distortion, a little bit of clipping, not a lot, but at least it showed the concept. But so if you don't have a potentiometer to use, you can fool around with fixed resistors, but it might get a little frustrating because you do have to hit. You either get lucky like I did, where it did work out. I just happened to, but the tolerances of the resistors and so on can make it to be a little bit tough. But you can definitely experiment a little bit with some fixed resistors. Maybe you'll get something oscillating. Maybe not perfectly distortion free, but that'd be a start to play around with the circuit. I'll show you how Hewlett Packard made their very low distortion sine wave oscillator. It's a great story. It is the Wien bridge oscillator. That's what they used, and they found a way to solve the Barkhausen criteria to match the one and just self-regulate. In other words, make sure that it could get the gain it needed, but if it tried to go over, the gain would go down, and if it tried to go under, the gain would self-regulate and boost. So it's sort of an automatic gain control that they added to this Wien bridge oscillator, and became the worldwide company that they are. So here's the cool story. How do you create a worldwide company? You just get a 50-cent little lamp, like we used in the first week of classes when we were doing our little circuits with lamps. And I'm thinking lamps are cool, and if any of you were thinking, that lamps are, beneath where you're at, take a look at this. This is all they did, and it was a very low distortion oscillator. Put them on the map. Cornered the market on sine wave oscillators with a little lamp put there for RI. And it has to be matched, whatever the hot resistance of that filament is, wouldn't necessarily be glowing full bright, but you would match your filament resistance with RF, and that should land at about exactly the gain that you need if you do the proper matching with the resistor. But here's the self-regulation of the gain. If the output tries to increase, do you see what happens? If this voltage tries to increase, that means the voltage across the lamp would try to increase. And if that happens, the resistance of the filament will increase. And if the resistance of the filament increases, RF over RI, the gain decreases. So an increasing gain, if it tried to run away, would increase the voltage here, which increases the voltage and current through here. And as that happens, the lamp's hot resistance goes up. And as the resistance of RI goes up, it pushes the gain back down. So it self-regulates. And vice versa. If the output would try to decrease, so would the voltage and current. And especially through RI, a decrease in voltage and current means its filament resistance goes down. So RF over RI, which is the gain, goes up. So it'll give a little boost to the gain. So it'll find itself a self-regulating circuit just with a little lamp. So pretty cool. And I don't know if you have any lamps laying around. Not any lamp will work. I mean, you have to get a lamp and a resistor combination that's going to work and match and all that sort of thing. But yeah, that's a pretty neat story. This is such a classic circuit, so um, it would make a great permanent build as a little paperweight on your desk. When you're out there in industry. I mean, it just to me, it puts together one of the coolest little simple networks slash voltage dividers. I think, and then if you add to it a little lamp doing your uh, gain regulation, it just is this is pretty cool, I think. And there are other ways to do gain regulation. Um, in your book, they'll show you one. You can have some additional RF here, which gets uh, the oscillator going. It would be sort of an additional gain if needed kind of thing. So here's your boost in gain. And then you use diodes, and you need diodes in both directions because the sine wave is going in both directions. But you would add diodes in both directions. I can draw a diode. And let's see if we can understand this. What's going to happen is here if it's going to regulate because if the output would try to get to grow too high, um, the IR drop across this resistor will start to bias the diodes on, and you have one in each direction, like I said, because it's the sine waves to take care of the positive and negative peak. But if the positive peak would try to grow too high, eventually it can't go higher because the positive voltage across this resistor would be growing and be limited to as soon as the diode starts to be biased on, it shorts out the resistor, um, and so that will bring gain back down. So as the output would try to grow too high, it self-regulates. It can only go so far, and so far, I mean, the limit to so far would be the voltage at the output that causes, yes, it's across all of these resistors, but it'll cause an RIR drop here that causes that gets when it gets close to 0.5, 0.6, 0.7. That's the end of it because uh, the IR drop will be turning on diodes that essentially short out the resistor and lower the gain. So it's another way you could regulate the gain. And I know I don't know that we have diodes. If you have any laying around, you can do this too. But those are all optional type exercises. Um, the self-regulation of gain. You can play with it if you have time, but or you can try to, just to try to dial it in carefully. But that you'll see how touchy it is. But either one of those, the lamp that Hewlett Packard used or this, you can get a very stable um, and very low distortion sine wave once you take care of that gain regulation. And like we said, I mean, this is just one way you can make a feedback oscillator. There are many, and you can always look some up if you're interested in fooling around. I have a handout. Um, Maybe next year I can get that to you since we're via distance right now. But that shows a lot of different ones you can try. Uh, all you have to do is meet the Barkhausen criteria. So whatever you're using for your feedback path for the positive feedback, you have to make sure you match the gain to it. Um, and so but again, it's just these ingredients. You're gonna to review it. If you want to create a feedback oscillator, first thing you have to do is create an amplifier, and then add positive feedback to it. And the positive feedback has a couple characteristics that it must have. It needs to be in phase. Okay, that's why we're bringing it to the non-inverting input. But your network here can't have phase shift, or I should say, it should have a net phase shift of 0. Because you'll see a phase shift oscillators that use um, a network that does have phase shift, but it all adds up to 0. If you have multiple phase shifts through your network, that the net phase shift is 0. That works. So as long as it's in phase when it gets to here, and meets the Barkhausen criteria and so on. So So lots of ways to cook up a feedback oscillator. And again, just as a reminder, um, you only need one scope channel for this circuit. You'll get it built, powered up. If you do get it to oscillate and you want to see that, I mean, we've been using channel 2 to monitor the output, so that's why I put channel 2 here. You might have channel 2 on your output. That's it. Don't go looking for a place to put channel 1. There is no input to monitor. We're not putting something in from the wave generator. We're generating a wave. So again, just that reminder. Just one scope channel is all you need to have a look at this thing. This isn't the first oscillator we've seen, so I wanted to put some things in context. You know, this circuit that we've shown you now is the Wien bridge oscillator, and it is a feedback oscillator, as we've described. If you think back, way back, when we were playing around with that little 555 chip, just to get some introduction to pulse DC and have a start, get a start on scope skills, you remember? We made an oscillator then too, and that was termed a relaxation oscillator. So relaxation oscillators are basically you know, a capacitor charging up and then reaching a threshold, you know, where it then starts to discharge down to a lower threshold. When it hits that, the circuitry switches so that the cap will start charging again. So when you have a cap, you know, winding up and winding down, charging and discharging, um, between two thresholds, that's important. You know, we said you can't have a single threshold; it'll just oscillate very rapidly, above, below, so like, you know, very high frequency noise. So you need the two thresholds, and then that would be your hysteresis. And if you remember, or with the 555, that's all built in. They had two comparators. You know, both watching the cap, one setting a high threshold to turn on the discharge path, and the other one setting a low threshold to turn off the discharge path and let it charge back up. So the cap, as it charged up and discharged between 2 points, that's your relaxation oscillator. And the output of a relaxation oscillator, you know, I mean, the output might be high and then low, and then high and then low. So typically a square wave, some kind of rectangular wave coming from a relaxation oscillator. So there would be some context for you. We now know two types of oscillators, you know, and there are others, of course. I mean, crystal oscillators use sort of a resonance of a quartz crystal. So that's an interesting, for another day too, of course, looking at, I think that's fascinating how people figured that one out. But yeah, the two that we have here, we've had some experience with. Just have to think back a little ways to that relaxation oscillator. Totally different mechanisms, for sure. So one last thing, if you're the curious type and you've been keeping track, you might have one more question, because we said the op amp by itself with no feedback, positive or negative, um, is maybe able to function well as a comparator. So that would be probably what it's being used for if you see it like this. So here we have a comparator, and then we said, well, you can add negative feedback and you'll have an amplifier. And then we said, if you have an amplifier and you add positive feedback, you get a relaxation oscillator. There's one other scenario that you might think of, right? So we have open loop. It's a comparator. Maybe I'll write these down quick for you so you can sort of follow, and then we'll add the final one. Think about it. So here I have it written out for us. Open loop, functioning as a comparator. Negative feedback, you can create a usable amplifier by reducing the gain. And also we played around with active filters. If you remember, we used an amplifier, and then we also used you know, a pole at the input to be the filtering action, and then go right into the amplifier. So active filters were built on top of amplifiers. And then in this session, we showed you if you have an amplifier from negative feedback, you can add positive feedback and get a feedback oscillator. So here we are with the last scenario What if you just give it positive feedback? And that means you're not really using anything to control the gain. So you still have that really high gain. Basically, you're still using it as a comparator, but you're going to bring, you know, some amount back. And, well, we can do it however you want, just the voltage divider thing, right? And this would be another session to to analyze this. But I think you can see I'm using the voltage division to bring back a certain amount of the output, but not back to where it will cancel, not back to the inverting input, but back to where it will be at the positive input. This is going to add hysteresis. And like I say, that's a whole nother session to analyze that circuit. But whatever your output is, you basically have a comparator, and what you would say is your reference voltage is coming from your output, so it's looping back on itself. So when the comparator is high, it'll set up a certain reference voltage, and then when it goes low, it'll set up a different reference voltage to be for this to be compared with. If that helps you a little bit to understand the hysteresis. So you have two thresholds. And in fact, those two thresholds, when you talk about a comparator that has two thresholds, there's a name for that, and it is a Schmitt trigger. So, didn't spell that right. Get that out of my way here. See if I can spell it right this time. Schmitt trigger. So that's what you have. If you take an open loop op amp functioning as a comparator and you add positive feedback, you've turned it into a Schmitt trigger. You could call it a comparator with hysteresis. And in fact, if you wanted to keep going, and this would be another session, of course, we won't analyze it, but sort of to tip you off a little bit, now that you've got two thresholds, you could certainly have a capacitor charge up and discharge, charge up to one and discharge to the other. I don't want to go, I don't know. I can double check this for you. How's this, Graham? Let's see. I don't know if I've drawn that right or not. So let me double check that. Hang on a second. Yeah, so okay, well, it's going to be something like this. But again, I don't want to start the whole next session. But bottom line is, comparator, add positive feedback, get a Schmitt trigger. You now have two thresholds, hysteresis. You can make a relaxation oscillator, and in fact, it would be something like this. The output here would be another oscillator. It would be back to a relaxation oscillator. Maybe real quickly, if the output's high, it's going to be charged. It's going to be doing two things. It's going to be charging the cap. It's also going to be setting a threshold for the cap to reach. When the cap reaches the threshold that's here, look what happens. The voltage at the cap will reach the threshold and go past it, and that means that this input is now greater because the cap just charged up past the threshold. As soon as this input is greater, the output goes negative. The negative voltage at the output does two things. It now starts to discharge the cap. It also sets a threshold, a negative voltage threshold for the cap to discharge down to. When the capacitor voltage falls below the new threshold that's negative set by the positive feedback, because the output's negative, which is discharging the cap, which is also setting a negative voltage threshold for the cap to get down to. When the cap gets below that threshold, look who's winning on the inputs. The cap went below this threshold, so this input is no longer winning. This input's winning. The cap voltage at this input is below this. So this is winning. The output goes positive, starts the cycle over again. The positive voltage starts to charge the cap. And away we go. we've got a square wave relaxation oscillator. So there, I got you 2 theory sessions for the price of one, and the second one only took a couple minutes. Now you're going to want that every time, right? 3 minute theory sessions. Why not? And I mean, feel free to fool around with it. I don't know if I am forgetting something here or not. It seems like it would work, but if I'm missing something, okay, we can catch that when we look at it in lab. Or I mean, this is optional, but I thought if you want to try with our 5 volt plus or minus 5 volts, you might expect somewhere around 3 volts at the output, a little more probably, but just to give you the idea, if the output's plus or minus 3 volts and you use 200 Ks or something like that, you could keep it simple for yourself, split it, send half of it back to the plus input. That would be our positive feedback. It's really the reference voltage because it's a comparator, and you would have the cap charge up to 1.5 and down to negative 1.5. I don't know. I just threw some values here, but maybe the 100 Ks slow things down nicely for us. But yeah, it's there. You could experiment with it and have that going on too. If you want to try it, go ahead. You could tweak the values. Let me know if it actually worked. So this finishes out our mini tour of op amps, and I mean, if you notice when you kind of take a step back, you really just you put an op amp on a breadboard. You have this building block, which is a pre-engineered amplifier ready to go. And then what do? You just sort of play around with all different arrangements of resistors and caps, just dancing all around the outside of it. I mean, that's really what it's been. And voltage division, really, a lot of the times. So, but it's a nice way to sort of summarize what that whole trip through op amp land is as we've done it, sort of just the basics here. Um, if you compare your different exercises and activities, yeah, you've just taken a handful of resistors and caps and just played around with all different arrangements. Whether it's to do a certain amount of negative feedback or to create a filter, a pole that's going to filter the input, or here as we actually wrapped up with one more example that I hadn't intended on, but I mean, here again, it comes down to a resistor and a cap. Now here it's charging and discharging, here it's of course voltage divider with a certain amount of feedback, or, we created active filters by putting filtering on the input of an amplifier, and then we used a filter in the feedback path to provide positive feedback for an amplifier, and we created a feedback oscillator. So yeah, I think it's a nice way to a nice statement when you get to the end is it's really been all about just you know splashing resistors and caps around in different arrangements around an op amp is what you wind up doing, and you can see how many useful things you can create.